So polynomials, you've seen two main kinds up until this point: lines and parabolas or quadratic equations. Here's the base linear equation, y equals to x. It passes through the origin, heads forever in that direction and forever in that direction. Here's the base parabola with vertex at 0, 0 and heading up forever toward infinity. And here's some new ones. The cubic graph, x cubed, looks something like this. It also passes through the origin. And you'll notice it's always increasing, except for right over there just briefly. It heads down toward negative infinity here and up toward positive infinity there. Here's the base x to the 4 graph. You'll notice it looks a bit like a parabola, except it's kind of squished in the middle there. It flattens down at the 0. And here is an approximation of the quintic graph or degree 5 graph. Again, it looks a bit like the cubic graph, except this has been flattened more. So you can see how this looks a bit like a line that's been flattened, and this looks a bit like a cubic that's been even more flattened. You'll notice some patterns here, namely the end behavior of these graphs. Odd degree graphs, such as the linear, cubic, and quintic, have the same end behavior, and by that we mean what happens as x goes on toward infinity. As x goes on toward negative infinity, this goes down toward negative infinity that way, and as x goes toward positive infinity, y goes toward positive infinity. And that's the case for all three of these. Whereas for these even degree functions, as x goes to negative infinity, y goes up to positive infinity, and as x goes to positive infinity, y also goes up to positive infinity. So we can extend this. If I asked you to sketch a degree 6 graph, we would take the degree 4 graph, same end behavior, and it might look a bit different in the center. The end behavior of a polynomial depends on two things. As we've already seen, the degree of the polynomial, as well as the leading coefficient of the polynomial. The leading coefficient is just another name for the a value. It's the very first coefficient on the highest degree. So I have an example here. This polynomial, the greatest degree term is degree 4. So overall, we say that it's a degree 4 polynomial. The leading coefficient is -2. The coefficient on that greatest degree term is -2. This one's a bit more tricky. It's in factored form. So be careful. The leading coefficient will end up being 3, but the degree is not 1 or 2 or 3. We have to imagine what would happen if we distributed this whole thing out. That would take too long to actually do. So lucky for you, you only worry about the very first terms. I know that when I square this, I'm going to get some x squared at the beginning, followed by some other terms. If I cube this, I get some x cubed at the beginning, followed by some other terms. And then if I distribute some more, finally, we can see that the very first term is going to be 3x to the 6. So after simplifying, we see that this is a polynomial of degree 6 and leading coefficient 3. So let's put this all together. We can determine the end behavior of a polynomial based off of its degree and its leading coefficient. If it's an even degree polynomial, either the ends will point up toward positive infinity or down toward negative infinity. Depends on your leading coefficient. If it's positive, it's pointing up, and if it's negative, it's pointing down. That probably makes sense to you because you've seen it with parabolas already. If you have an odd degree polynomial, they always point in opposite directions. If your leading coefficient is positive, I think of it as the graph is increasing. It starts down here and it heads up this way. So from negative infinity up toward positive infinity as you move from left to right. If the graph has been flipped, it switches. It starts way up here and comes downward, so that it starts in this quadrant and would end down in that quadrant over there. So some examples. We see that this is a degree 5 polynomial, and its leading coefficient is negative. It's -2. So I'm not really sure what's going to happen in the middle here, and we'll soon enough see what happens in the middle when we start transforming these graphs. But I do know that it's going to start way up here and somehow head down and tend toward negative infinity in that direction and positive infinity in that direction. Down here, I have a degree 6 function, right? The highest degree on any term is 6, and the leading coefficient is +4. Therefore, I know this graph will tend toward positive infinity. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y also goes to positive infinity. Again, don't know what happens in the center. We'll come back to that later. So the zeros or x-intercepts of polynomials. Again, you're already familiar with lines and parabolas. We know that a line can only have one x-intercept or one zero. There's no way a line is ever going to cross the x-axis more than once. You know that parabolas or quadratic functions can have no zeros 1 0 where it just bounces and heads back up again, or 2 zeros where it passes straight through the x-axis at 2 points. Now we can generalize to cubics, quartics, quintics, etc. A cubic function, it's impossible for a cubic function to have no zeros, because otherwise we couldn't get this end behavior. There's no way a graph could tend down to negative infinity and up to positive infinity and have no zeros. So the minimum number of zeros for a cubic is 1. We can also get 2, where one passes right through and the other one just bounces. Or we can get 3 zeros, where at each of the 3 zeros our graph just passes right through. Now in a quartic, as you can see, we can get no zeros, where we just get that kind of parabolic shape that's been smushed. We can get 1 0, where it just bounces. We can get 2 zeros, where it just bounces twice. We can get 3 zeros, where it bounces once, crosses through twice. Or finally, we can get 4 zeros, where it crosses right through at 4 different points. So we can generalize this. An odd degree polynomial must have at least 1 0. Once again, we can't get that end behavior unless it has at least 1. An even degree polynomial can have no zeros. The maximum number of zeros for a polynomial is simply the degree of the polynomial. A line may have up to 1 0, in fact it has 1 0. A parabola has up to 2, cubic up to 3, and a quartic up to 4, etc. So here's an example of a degree 6 polynomial. Once again, if you distribute this out, this is squared, this is cubed, and this is linear, and multiplying all of those together, we'd end up with a degree 6. It has a positive leading coefficient of 1. Now, we can solve for the zeros by setting each of the factors to 0. There's a 0 at -1, +3, and +5. These two are special. They have a little exponent on them, right? When a factor has an exponent on it, that is not 1, your graph is going to do something funny at the 0. So I've sketched an approximation of this graph. You'll notice I didn't label the y-axis. We've always told you that that's bad. But I did it on purpose. We don't know how high or low this graph is. We're just kind of guessing. Unfortunately, we're going to need calculus to graph this a little bit more precisely. So for the time being, what we're concerned with are zeros and end behavior. So there are my 3 zeros that I said above, -1, +3, +5. -1, we say, has order 1. It didn't have an exponent on it. So my graph just passes right through. At 3, well, that factor had a little squared on it. We say that that 0 has order 2, and as a result, on the graph, it simply bounces off. So it still has a 0 there, but instead of the graph going from negative to positive or positive to negative, it would stay in the negatives. And lastly, an order 3 0. Your graph passes through, but as it passes through, and it may be a bit tricky to see, the graph flattens. So it goes through, flattens slightly, and then continues on its way. The way to remember it is if you zoom in on the 0, the order looks a bit like that graph. An order 1 0, if you just zoomed in there, would look like a line. An order 2 0, if you just zoom in there, looks a bit like a parabola. And an order 3 0, if you just zoomed in there, would look like the cubic graph. Of course, we can continue on to quartic, quintic, but we're not. So finally, let's just do this whole example from the top. We've got this polynomial. It is degree 5. This has degree 1, 2 makes 3, 4, 5 altogether when we multiply. The leading coefficient is +1. I have a 0 at 0, -1, +2, and +4. Only one of these zeros is different, is special. This one, we say that at -1, the 0 is order 2, so it's going to bounce. What is the end behavior? Well, degree 5 and a leading coefficient means it'll start down here from -infinity and head up toward +infinity. So putting it all together using the zeros and end behavior, well, the end behavior was down toward -infinity this way and up toward +infinity that way. Here are my 4 zeros, -1, 0, 2, and 4. And one of them, -1, had order 2, so I make sure to bounce my graph off there, don't let it pass through, while at the remaining 3 zeros, my graph passes right through.